Hello, my name is Thi Tuyen Ngo. I'm currently working at the Multifunctional Optical Material Group of the Nanoscience Institute of Sweden. And today, I'm going to show you my later work with the title of Converting photomaterials based on radar elements. First, what are photomaterials? They are the substance which has luminescent phenomenon. Naturally, we are very attracted by those materials because of their different emission colors. Not only that, the photomaterials based on radar elements are very important. They are part of high technology. For instance, some high technological products like smartphone, television, and computer are nowadays very common and absolutely necessary. The brightest color displays on the screens are produced by small amounts of photomaterials based on radar elements. And for some radar elements, until now, has no substitution. For example, European, which has been used as a red phosphor in television. Moreover, radar photomaterials have been used in industry to produce lamps. That is a very important product that we use to illuminate houses, offices, etc. Moreover, the photomaterials based on radar elements also contribute to the fabrication of specialized industry. For example, to produce lasers with different colors, or to fabricate anti-forgery masks or aerobinos. Photomaterials based on radar elements have diverse applications. So what are radar elements? There are total 17 elements, including yttrium, holmium, erbium, etc. Despite their names, radar elements are relatively plentiful in Earth's crust. They are often found in minerals. Those elements differ from the others. In terms of chemical properties, they are almost exactly the same. They seem to be inseparable. However, in terms of electronics and magnetic properties, each element is unique. The use of radar elements has been increased quickly over years. There are many kinds of products based on radar elements. However, today I'm focusing on only upconverting photomaterials. The upconverting photomaterials are the materials which absorb several photons with low energy, in general in the infrared regions, to give the emission photon with high energy, in general in the visible range. The reason for why we are very interested in those materials, because they can be applied in many different fields. As mentioned before, upconverting photomaterials can be excited by infrared light, which has very low energy. So they are very suitable for drug deliveries and therapeutic applications. Because we don't need to use high energy to excite the materials. Therefore, we can reduce the damage for vivo cells. Moreover, if particles of upconverting photomaterial exhibit good brightness and uninterrupted emissions, so they allow a long-term attracting by molecules. For complex systems like protein, it's very important to distinguish and visualize different parts of the system at the same time. So the possibility of tuning different emission colors of upconverting photomaterials is very suitable for multiple targets of biological imaging. Upconverting photomaterials can be used as a photodetector as well. They can absorb the photon infrared range, which are invisible, and convert them to photon in the visible range, which can be seen by human eyes. So upconverting photomaterials can be used to prepare laser viewing cards. They were useful to make an optical setups using invisible lasers. Solar panels are nowadays very common, and they have been used to produce electricity from sunlight. A solar panel has many solar cells. Each solar cell has an absorber material. The efficiency of solar cells is limited by the absorption of the absorbable materials. Solar panels nowadays on the market are mainly based on silicon materials. However, silicon doesn't absorb well the spectrum of solar, especially in the infrared regions, while the converting photon materials can absorb the photon in the infrared range and convert them to the visible range, which can be absorbed well by silicon. So the introductions of converting photon materials in solar panels can help to improve the efficiency. I have shown you a few examples of application of converting photon materials. In general, they're composed of a host matrix with doped by radius elements. The host matrix needs to have low photon energy to reduce non-relative loss and to maximize the relative emissions. The most common use as host matrix are based on fluoride. The dopant ions in converting photon materials will absorb the energy of excitations and give the emission. They are classified as activators and sensitizers. The activator ions need to have the energy diagram like lattice structures. The reason is the activated ions will absorb several photons of excitation which has the same energy to be excited in the high energy states. And from those states, when they decay to their ground states, they will give the emissions. The most common use as activators are erbium, thulium, and holmium ions. However, the activator ions had low absorption cross-sections. So in order to improve the luminescence of our converting photon materials, they usually coupled with sensitizers, which has much higher absorption cross-sections. The most often used as sensitizers is terbium ions. In the cold system, terbium ions will absorb the energies of excitations and transfer them to activators to excite them to the high energy states, and when they decay to their ground states, they give different emission colors. Now I'm going to show you the experiment part that we are doing in the laboratory. In order to prepare our converting photon materials, we make a synthesis. It's very simple. We just put all the precursors together in a tube and heat them. With the temperature and times, crystals form and growing. This is the particles of our converting photon materials. They are very uniform with an ellipsoid morphology, and the average size is 130 nanometers. Single human hair is a very small object that can be seen by human eyes. This size is much smaller than 1 millimeter. However, if we compare single human hairs with our synthesized particles, it's really big. It can be equal to the length of 1,000 particles. So you can imagine how small our particles are. Once we have the particles of our converting photon materials, we prepare a film by spin coating method. We drop the particle suspension on the substrate and spinning. The thickness of our converting photon films can be easily tuned by changing the concentrations of particle suspensions or modifying the spinning speed. We also can repeat this process several times to increase the film thickness. Once we have the films after spinning, we make a thermal treatment to hint the defects. This is the top view and cross sections of our converting photon films prepared by a spinning method. It's very homogeneous with the thickness in the range of 1 micrometer. From the top view, we see the porosity structures, which is typical for the film prepared from the particles. And if we pay attention, the morphologies of particles after the annealing is very similar to the particles after the synthesis. In order to measure the emissions of converting phosphor films, we use an infrared laser to excite the samples. Its emission is collected by the detectors which connected to the computers. This is the photoluminescence of the erbium materials. There are three different emission bands: blue, green, and red emissions. The emissions are corresponding to the transitions of erbium ions. And because of the red emission is the most intense one, so from the naked eye we see a bright red light. For the case of holmium samples, we observe two emission bands, the green and the red emissions. They are also corresponding to the transitions of holmium ions. The combinations of the green and red emissions give us an orange light. For the case of thulium samples, there are three different emission bands, the blue and two the others in the IR. Those emissions are fit with the transitions of thulium ions. And because human eyes are not sensitive with the emission in IRs, we observe a blue light for the samples. This is the absorptance of converting phosphor films. We observed an absorption peak at around 980 nanometers, which fits well with the transitions of ytterbium ions. Important to note that when we use a laser of 980 nanometers to excite the samples, we observe the emissions which are corresponding to the transition of activator, including erbium, thulium, and holmium. So the detection of the absorptions of the ytterbium and the emissions of activators confirm the energy transfer conversion process that I explained before. When we compare the emission intensities of the sample doped with different ions, we found that the sample doped with erbiums give the highest luminescence intensities. So it means that the energy transfer process from ytterbium to erbiums is more efficient comparing to the system of thuliums and holmiums. If we pay attention to the energy band diagrams, we see that the excitation test of ytterbium is much better with the intermediate energy test of erbiums comparing with the thulium and holmiums. This should be the reasons why the energy transfer process from ytterbium to erbiums is more efficient comparing with thuliums and holmiums. We already have different emission colors obtaining from converting phosphor materials. So next step, we would like to combine the different emission colors with proper properties to generate a white light. To summarize, I already showed you what converting phosphor materials are, the components, and the mechanism of converting phosphor materials. I also explained why the converting phosphor materials are very important by showing the application in different fields like biomedicals, photodetectors, and light harvesting. I also show you the experiment part that we are doing in the lab, including the synthesis of converting nanophosphor materials and the film preparations and the optical characterizations. With this, I would like to finish, and I would like to thank all the people in our group for their contributions. I also would like to thank all the funders for the financial support, and thank you for your attention. I hope you enjoy it.